Okay, thank you everybody for coming to the AI seminar today. My name is Nathan Sturtevant, and I'm going to be giving a presentation today with Arda. And Arda will do some introduction. But I want to give you some context for this talk because this is a talk we gave last week at the Game Developers Conference in San Francisco. So the Game Developers Conference is there were 24,000 people there this year. And inside that, there was an AI summit for people that were interested in AI. Maybe about 500 people were at the AI summit this year. And so we want, when we heard that there was a slot this week, that there was an open spot, we said, well, hey, we just gave this talk to this big game developer audience. Maybe we should come give it here because I think there's some interest. But the audiences that the talk is designed for is a little bit separate than our audience here. So Arda's done some work to try and modify some things, but I would say go ahead and interrupt us at any point. If there's something you're like, I have no idea what you're talking about, this is totally confusing, that's understandable because, as I said, this was not designed originally for a, sorry, I'm trying to hide my Zoom controls, for an audience that isn't in the game development community. So we'll do our best to adapt it on the fly, but if you have any questions, just feel free to answer those or ask those questions. And with that, I'm going to turn it over to Arda, who's going to give some background on Inflexion Games, which is where this work has been done and what he's been working on.
Hello, my name is Arda Saifi. I'm currently an AI programmer in Inflexion Games. I graduated from this university about 3 years ago with a master's degree in AI. Today, we're going to be talking about the work we did on creature movement and spawning in our first game at Inflexion Games called Nightingale. So typically, creature movement and spawning are just challenging problems on their own, no matter what game it is. But when the games are procedural in nature, meaning there's a lot of randomness that you have to account for, the problems become even harder. So we're going to cover some of the techniques we came up with and some of the challenges we faced while developing this game. So we are from Inflexion Games. Our studio is right downtown on 104th and 102nd. It's right above Dusk. The studio is about 130 people large, and our team's hybrid and remote. We got people from all over Canada and even in the UK. The studio was founded by Aaron Flynn in 2018. Aaron was a previous head of studio at BioWare, and he went away and started the studio. And we haven't released the game yet, but it's set to release this year. The game's called Nightingale. So an overview of this presentation, we'll begin by introducing Nightingale. Then the majority of the talks actually spend on our navigation technology, namely our abstract graph. And then we'll talk about how we make the realms feel alive with wildlife and how we accomplish that using k-means clustering. So the takeaways for this talk. So we're going to show you how you can add an abstract graph on top of a navigational mesh, which we'll describe later on what that is if you don't know, to achieve longer distance pathfinding with terrain preferences, and how you can do more efficient custom queries, such as finding the closest unit. And we also talk about our connectivity graph, which you might know as connected components if you've worked in this space before. Lastly, we'll show you how you can use k-means clustering to evenly distribute creature populations in a three-dimensional space. So to introduce Nightingale, here's one of our trailers.
For you, the year is 1889. The world as you know it teeters on the brink. The magical network of portals has collapsed. Your people are cast asunder beyond the frontiers of your reality. Realms alive with monstrous beasts, eldritch creatures and dangers of which you cannot conceive. You must gather your wits, craft whatsoever you require and build a life in the realms. Uncover the secrets of realm cards and venture deeper into the unknown. Your path forward is winding and full of terrors. Save yourself, survive the realms, and rebuild all that has been lost.
So what is Nightingale? Nightingale is a co-op survival crafting game. If you don't know about survival crafting games, the gameplay is around the player crafting better items, gear, and equipment to survive in tougher and tougher environments. The emphasis in our game is on traveling to many different procedurally generated realms. Now, realm generation is directly modifiable using the realm card system, which you mentioned in the trailer. For example, you can play cards that will add or remove creatures, increase or decrease creature density, and you have many, many other options as well. The game is built using the latest version of Unreal Engine 5. So here's some footage of our realms. This is a forest realm. This is a swamp realm. And this is a desert realm. All of these realms are fully procedurally generated. What we have is we generate a realm template offline, and then at runtime, we fill these realms with content based off of some rule set that we have defined. Now, each of these realms have various terrain types, like shallow water, deep water, they have a road network. We even have things like high sloped areas. Now, we want our creatures to be able to respect these terrain types. For example, don't go into deep water, follow the road, or try to avoid high sloped areas. Our environment is directly modifiable by both AI and the player, as they can add or remove objects from them. So here's some of our creatures in the game. These are our critter class creatures. For example, this is Mepigal. We also have wildlife creatures. We have the Bandersnatch, the Wine Elk, the Burpo, the Desert Yone. You might have seen some of these in the trailer. We also have the Bound faction, and their whole purpose is to just hunt down the player. Here you can see the Flame Spitter, the Bruiser, the Lanternhead. Now, fun fact, I actually got into a mocap suit for the Flame Spitter there and the animations for it. So that flamethrower animation you see there, that's me. Also, we have monster class creatures, such as the Jotun, the Harpy, and the Carnute, all of which are in the trailer, and the Apex class creatures like Ishmael. These are our most complex creatures. So let's talk about our navigation system. So the guiding principle while developing our nav system was that an efficient navigation technology will enable fun gameplay opportunities. So before we go into it, I'm going to describe what a navigational mesh is. So consider you have the following scene. This is what the nav mesh underneath that scene looks like. So a navigational mesh is used for pathfinding in complex terrains, meaning just non-grid based pathfinding. So as you can see in this picture, the nav mesh is generated using the meshes you put in that world. And it is comprised entirely of 2D convex polygons. So then to find a path from point A to B, what we do is we perform an A-star search on the triangulation of the polygons in the nav mesh. And then to actually perform that path, we just follow along the edges of the path it gives us. Something else that you will need to know is that a nav mesh can be marked up with what we call nav areas or terrain types. So for example, here I've marked up there that area as a navigation area. A navigation area can have different weights for entering, for exiting, for staying in. And that is how you can get creatures to path differently based on different terrain types. So here's a small section of one of our forest realms. You can see a few structures. You can see many different rocks and trees, some road there, some water. This is what the nav mesh underneath all of that looks like. As you can see, the nav mesh is quite rough. There's many polygons. In some of these tiles, there's many, many polygons. And you can see our various terrain types, at least some of them. The road there in red, the water in blue, the high sloped areas there are in orange, and the default there is in teal. Something else you might notice is we have what are called a lot of navigational islands, nav mesh islands. For example, at the top of the structure there, that nav mesh is not connected to any other nav mesh. We refer to those as nav mesh islands. We have several thousands of these, and they pose problems. And we came up with some solutions for dealing with them, which we'll cover later in this talk. So an overview of the whole navigation system in our game. We use Unreal Engine's default pathfinding system. It's called Recast or Detour because it supports all of the requirements of the game. But we found that during development of the game, it just wasn't efficient enough for many of the use cases we had. So what we did is we've built an abstract graph directly on top of Recast, and it supports all of the gameplay needs we've had thus far. Some of this work was published in conference in 2019 by my co-speaker Nathan in collaboration with the Inflexion team. So now I'm going to invite Nathan to come up and explain the abstract graph and some of the benefits it brings us.
Okay, thanks, Sarda. So I started working with Inflexion when they were founded, or right after they were founded in early 2019. And what we did at that time is we sat down and we basically started to brainstorm what were the high-level gameplay features that we wanted to see in the game. What was it that they, like with large creatures like this, to be able to move through the world, to move efficiently, to respect terrain types like Arda was talking about. And then based on those requirements, what we wanted to do was build a navigation technology on top of what was existing in the engine, on the Unreal Engine, and be able to use that to get the gameplay opportunities that they wanted to see in the game. So, so we started, in particular, though, we started this level of design. What are the interesting designs we want to see? What are the interesting behaviors we want to see? And then, as Arda said earlier, the most important premise is that if we design efficient pathfinding technologies at the very bottom of what's being used, then it's going to enable much more interesting technologies on top. So what I'm going to do here before I get into the technical details, and I'm not going to go in spend a lot of time on the technical details of what we did, but I'm going to spend some time talking about some of the things that we can do as a result of this technology that we have of using this abstract graph. And the other thing I'll say is that abstract graphs have been used, like I put them in Dragon Age. So this is a very similar thing that we did in Dragon Age about 15 years ago. When we were at GDC, the person who wrote the pathfinding for StarCraft, the original StarCraft, came to talk to me afterwards and said, yeah, they did something similar as well in that game too. So these are known ideas, but what we're doing here particularly is having to deal with a world that is procedurally generated, and also having to deal with the terrain costs that we have, a dynamic world and terrain costs on top of it. So the first benefit we're going to get from having an abstract graph is we're going to be able to handle terrain preferences efficiently. And to show this off, what I'm going to show is the contrast between the default system. So Unreal 5, there's a number of different game engines that are available. Unreal 5 is sort of one of the leading engines that's used for AAA games. There are some other engines out there, and different studios have proprietary engines and things like this. But Unreal 5 is an engine that is very broadly used, has some of the highest quality graphics out of the box. And inside it, there is somebody who wrote an open source engine called Recast. There's a path planning system inside it called Detour. And that's what has been integrated to Unreal. It's been integrated into the Unity engine. It's very widespread. If we take that default thing that's sitting inside the game, and here we're going to have a simple example of a creature here in red, and the creature we want to ask it to pathfind up to the top of the map up here. In this case, it happens to be a vine elk, and it's pathfinding up here to reach Puck, who was the advisor for the character that we see in the trailer. And if we ask Recast, default out of the box, find us a path, it's going to give us this path. So there's a couple of things we notice here. One, it doesn't give us a complete path because it runs out of its budget of how much work it can do per frame. Because games are running real time, there's only so much we can do in one particular frame of the game. I mean, in this case, it would maybe have to replan over multiple frames. The other thing we can notice here is that Recast is essentially doing a dead head. So this is a world that, like, yeah, you can really walk anywhere in the world. It's just we don't want you to walk some places, and Recast is sort of trying to walk straight towards the goal. But when we put our abstraction system on top of this and ask it to do a path plan, we end up getting a path that looks like this. And what's going on behind the scenes, if we look underneath here at the coloring of the nav mesh, what we see is that actually there's this road network on the map. And when we use this abstraction, we're able to efficiently go find the road network. We discover that the road network for this particular query is less expensive to travel. So then we go travel on this road network and we're able to get all the way to our destination within the time requirements that we have. So the first thing here just to say is we're able to now support costs in the world and do efficient pathfinding even when there are costs in the world. Something that basically most games can't do, or the game engines can't do out of the box. If it's going to be in a game, someone's going to have to be able to support it to be done more efficiently. The second feature I want to show is not only do we support costs out of the box, or on top of what it comes out of the box, but we're also going to be able to support costs on a per creature basis. So dynamically at runtime, I can change the cost for any given creature in the world, and the creature will change its behavior accordingly. So it's not something we have to bake in and like once it's set and everybody's going to travel, but we can do this dynamically at runtime. My screen's here flashing. That one's not flashing. That's fine then. Okay, and so we're going to do another example here. So in the bottom left here, we have a bound. This is a bound lantern head. So this is Arda. And he's trying to get, again, to Puck here, who is our guide through the world. And the behaviors that the designers have chosen for the bound is that the bound don't care about anything. So the bound are essentially giving us the normal behavior that we expect of just get to the goal. I don't care what type of terrain you get on. We're just wild creatures. That's the behavior we want. And so we go in that example and we run Recast, we run our abstraction. Both of them solve this problem. They both come around the rock, so they can't jump off the cliff because there's too great of a height difference there, but they can come around here, they can go through the water, and they can get to Puck here. And we can see the different terrain types. So there's a road here, there's the water, and then Puck is on this little peninsula sitting there. So that's fine. That's sort of the default behavior you see in most games. But we can come to another example here, going back to a vine elk. So now we have a vine elk over here, and the vine elk wants to get to Puck. The vine elk does not want to walk through water, or at least to the shallow water here. So what's going to happen? Well, now when we ask Recast to find a path, it basically comes up to the edge of the water and says, sorry, I can't path any further. I'm stuck here at the edge of the water. That's all I have time. Because the water is more expensive, the heuristic that's guiding the search doesn't know that there's water there. In fact, we don't have time to pre-compute that. And so the search basically runs out of resources at that point. However, when we use the abstraction, because the world is represented so much more compactly, we can actually find our way on this road, going all the way around Puck from the other side, get onto the peninsula, and complete our path. And it's actually really important here that we are able to complete our path, because we'll see later, it makes a big difference if I give you a partial path versus a complete path with the type of queries we can do in the world. Okay, so again, this is what the nav mesh looks like. Recast got stuck at the edge of the water. And what Recast is doing is it's saying, look, I did a big search here, and this is the closest point I could get to your target in the time that was allocated. So the search could actually is doing a lot of other work, looking in a lot of other places, but this is the closest point it found. And that's what it's giving back to us at the end. Okay, and we can see here then, if we look at the underlying nav mesh, we can see all the triangles and polygons that are sitting here in the world. And then we can also see the abstract graph. It's a little bit hard to see on this slide. We'll have another slide later that's clear, but we can see this abstract graph is a lot more sparse than what we have in the original nav mesh. And I'll explain that in detail momentarily. So the third thing I'm going to show you is a benefit that we get from this abstract graph is actually we're going to combine it with a specialization on the A-star algorithm that's going to allow us to do some custom path queries. So what's used very often in games is I need to do things like, what is the nearest creature to me? Because like maybe I'm going to go attack the nearest creature or something like this. And so when I have things like that in the game, we have a couple of options of how we could do that. One thing we could do is use something that's called an EQS system. EQS is an environmental query system, and it'll look around, it'll find the creatures. And for instance, we could just measure straight line distance to creatures that are close by. So for instance, if I'm standing right here, there might be a creature that's standing up on top of this rock, and I say, yeah, that's the closest creature to you in terms of absolute straight line distance. And so a lot of games will do that, but it can result in poor behavior because the absolute straight line distance doesn't actually represent the pathfinding distance in the world. That is the path that we would actually have to take. And so what we want to do is we want to use the fact that we have an efficient pathfinding system to be able to answer these queries actually much more accurately. And there's a bunch of ways you could solve this problem. So we have, let's just say we have two other creatures here. One is over here on another peninsula. It's surrounded by water. You can't quite see it here because of the trees, but there's water coming around there. And we have another creature that actually looks like it's quite far away, but there is a road that's actually connecting them directly. So maybe we'll be able to find out that even though that creature is the farthest away, in terms of actual distance, it's not so far. So how do I solve this problem? Well, I could just say, like, I'm going to do an A-star path from my start location to each of these locations, and then I'll just choose whichever one's closest. But that feels inefficient because I'm doing 3 searches, but the searches are sort of overlapping. And then you could, on top of that, you could try and do some optimization, like, well, I'm going to start searching, maybe I'll search on all of them. And then, if one's making more progress, or if I find one, I can cut off the others. It ends up that although we could do that, A-star has this ability to actually do it all for us automatically. And the answer is for A-star is, instead of searching from myself to 3 possible targets, we put each of our targets into the open list of A-star, and we search in reverse from the targets back to us. And when the search completes, and only when the search completes, so this is why it's important that the search does complete. When the search completes, then I can just trace, I'm going to get some path to myself. I trace it backwards, and that'll tell me which of these 3 was actually closest to me. So in this example, what would happen here is we'd start searching. So A-star will search from the one that looks to be closest, according to our heuristic, which is a straight line distance. And then you discover, oh, as I begin to search there, my search actually starts going in the other direction, and all of those locations look unpromising. So at that point, it looks more promising to start searching from the second creature. But here, again, because this is a survival crafting game, I don't want to get my player wet to find a creature. In fact, this is actually a spell in the game that you can cast, which is find the closest creature, and it's going to guide you to get to that closest creature. So for the second creature, you discover there's water there. We would prefer not to get the player wet if we could avoid it. So that doesn't look promising anymore. But then A-star will start searching for my third creature here. And on my third creature, it'll actually discover it's on a road. I'm not far from that road, and it'll find that path very, very quickly. And so then it'll return and be able to follow that path. So what's important here is actually not only having these efficient low-level navigation technologies for finding paths helped us in that regard for being able to respect terrain types and having different terrain types for each creature, it's also helping us do specialized queries for other things in the game. So if you get the game and play it, you can cast a spell, and this is actually what's going on behind the scenes. So now let's talk a little bit about how this is actually being done in practice. And one thing here that's helpful to know is how recast as a system. So recast is a system that takes all the polygons in the game and says that I'm going to take those polygons and I'm going to measure and find the walkable areas in the world. And one of the things it does to do that efficiently, what it actually does is it sweeps voxels through the world, and then it reconstructs those voxels into polygons. And one of the things it does to make that efficient is it does it on grid. So it divides the world up into grids, and then on those grids in the world, it finds all the polygons, and it can do those independently. One of the reasons it does that is so when the world changes, you don't have to rebuild the entire world, but you only have to rebuild the localized grids that changed. And of course, you could build grids inside here, but using polygons is generally a more efficient representation. So what we might have in the world is something that looks like this, which is one sector of the nav mesh, which is broken into polygons, and each of those polygons are of a different type. Now, this is sort of a worst case example. We'll show this in a couple of slides. I'll show you sort of the typical example that shows where this is helpful. So what we're going to do is we're going to divide up in the world. We want to group together all the polygons that are of the same terrain type that share a border with each other. So for instance, here in the upper left-hand corner, all these polygons are the same type, and they share borders with each other. So we're going to call this region 1. On the bottom right, we're going to call this region number 2. We're going to go back up. There's water on the upper left, and there's water on the lower right. So those are regions 3 and 4. We have this road in the middle, so that's going to be 5. And then we have these 2 little regions in the upper left and bottom right corner, and those are going to be 6 and 7. And what we're going to do is we're going to turn each of those into a node in a graph. And so we're going to get an abstract graph in this case, which is going to have 7 nodes here, which represent each of the locations and each of the terrain types in the world. And then if there's any 2 terrain types that share an edge, and this is done both inside one of these sectors and also across the borders, then we're going to add edges between them. So in this case, we get an abstract graph that looks like this, and it represents the terrain in the world. And so we'll be able to, and I'll show some examples in just a second, but we'll be able to do pathfinding on this. But the important thing is that terrain type is directly represented in the world. When I find a path through this graph, I know exactly what types of terrain it's going to go through. And that means that at runtime, I actually can change the cost of different types of terrain, and I'll be able to reason about it directly in the world. So this is something, it may seem obvious here. Actually, someone came up to me after a talk at GDC and said, what an obvious idea. I don't know why anybody hasn't talked about this before. Well, so we presented a paper on it, 4 years ago when we first designed the system, but now as we're getting close to ship, we can finally talk about it more broadly, and maybe other people will adopt it as well. Okay, so let's look at the first, going back to this example that Arda was showing earlier. This is an example where the nav mesh has around 200,000 polygons on it. And 200,000 is probably typical for sort of your larger game. I was talking to someone who's like, yeah, we hit 200,000 sometimes, but we would prefer to have more like 50,000 polygons in our world. So that's sort of, it's not like we're setting something way smaller. We're also not orders of magnitude larger, but that's approximately the size that many games are today. When we take these polygons and run the abstraction procedure on it, we end up with 50,000 nodes. So this is the abstract graph. We end up with 50,000 nodes in the abstract graph. Yes.
I can't quite see it here, but I would think like the road, all this one big particular segment of the identity. Why is that not one node in the abstract graph? It doesn't look like it is.
Sorry, let me go back. So you're saying like the road here?
Yeah.
So when the recast system and any system that's trying to take a whole bunch of polygon soup and turning it into a pathfinding representation sweeps through here, like it's got it, so like the other terrain that's sitting inside one of these sectors, it's got a particular shape, and the way the obstacles are, it's got in some way that it's just got to break that up. Okay. Sure.
That way you describe how the road could now be the entire road sequence is one.
So inside each sector, the road sequence is 1 point. So if we look at these roads here, what's actually happening, so on this one, the owl's running, right? So we think about one of these right here, this is going to become 1 point for this piece of the road. And here there'll be 1 point for this piece of the road. So in each of these pieces of the road, there'll be 1 point. And then, but there is connectivity here. So when the road, for instance, splits this area, you're going to have a piece here, a piece of the road, a piece over here, which is why we see the extra edges in the world, because of the borders that are being shared. Does that answer your question? Or you're frowning? Okay, so when we look here, actually, you can see this. This is the road. These are all the nodes here that are representing the road. This one is probably this one. And these are representing like the other areas of open space. And there's one of those, here, there's one for each abstract node.
Yeah, I guess I'll try one more time to see if I can.
Okay.
I thought the way you described how you were going to find the abstract node. Basically all the polygons that share the same frame type and were adjacent.
Oh, yeah, but we only do that on a per sector basis. So we'll do it for one sector, and then the neighboring sector, we do the same thing, and then we connect them. Yeah, okay, good. That's exactly why, yeah, no problem. It's a really good question. Now, the reason why we do that, we could get all of them to be one node, but the problem is that Art is going to talk about what we do when we repair the world. The world's going to change all the time. And if it's one node, then we have to look at the whole world all the time, anytime anything changes. And there's a lot of changes going on, which is actually why this is the solution that works really well in the world. So the other thing I want to say here is we see a factor of 4 reduction here. So the basic level you'd expect on average that we're going to get a 4 times reduction in the number of, or 4 times, basically you can search 4 times farther in the abstract graph, or it's going to cost 4 times less. But this is actually a little bit of deceptive because if you look in this world and you see these orange areas, the orange areas is areas of high slope. The high slope areas are almost always by themselves. You don't have big areas, like you get a polygon of a high sloped area. I don't know if my mouse shows up here. Oh, I can get it this way. But anyway, I'll walk over here. So right, each of these are like high sloped areas and they all abstract into a single node. And so of these 50,000 nodes that are there, something like a third of them are just high sloped areas that abstract from one polygon to one abstract node. And what that means is actually in the rest of the map, we're actually getting a much larger savings. And so let me show that here. I also want to show one more thing here, which is a gameplay feature that you can do. So this is a road through the world. Now you might be thinking the road might be going down here, but it's actually not. There's a road going from left to right across here. And that is to say, in a game, we can designate roads in the world that are not roads that the players see, but they're roads that create behavior. If creatures are moving through the world, this is where the creatures are going to move. This means in terms of a gameplay experience, I can learn where the creatures tend to go, and I can, and I can go there, and I will tend to interact with creatures when I'm in these sorts of places. So this is an opportunity for players to be able to learn about where interactions take place without having to explicitly mark everything up in the world. So here's the road. And so this is the representation here. And what we see here is, well, this is a world that's actually broken down into quite a number of polygons. But when we think about the abstraction, well, there's one node on top, there's one node in the middle, and there's one node on the bottom, right? So we're either above the road, below the road, or we're on the road. And here we've taken dozens and dozens of polygons and made it into a very simple procedure of just saying, like, do I want to follow the road or do I want to get off the road? And so that's, in this case, it'd be dozens of times cheaper than trying to use the polygons directly. And then there is a procedure. Well, we'll talk about it in a second, or I'll refer to it in a second, of how we actually turn this into a real path in the world. Okay, so this is actually how it occurs. So how do I do a path in the world? Because this is really important. Actually, an end-to-end path is that now becomes a little bit more complex, but it already actually was a complex procedure. So what's going to happen here is I'm going to get a start location in the world. I'm going to get a goal location in the world. So what do I do? The first thing I have to do is do an abstraction step where I say, from my start and goal locations, I need to localize onto my abstract graph. So I have to know from the low-level world how we get on the graph. In our case, we're running on a server. We have plenty of memory, so we just store that explicitly. Again, I was talking to some other people. They were saying, could you get that memory down? Well, yeah, you can do it. There's a trade-off between basically time and speed. So you can figure it out computationally, or you can just store it and not have to figure it out. But anyway, somehow we have to figure out where we are on the graph. Once I know where I am on the graph, so this is going to turn into search from a node on the graph to a node on the graph. We can then do a pathfinding request on this graph to say, how do I get this path? And then given that I have a path, the path, of course, now I need to turn it into something I can walk in the world. I know generally where I'm going to walk, but I don't know completely. So what this gives me is it gives me a strip of polygons. And now we can go back and say, now find a path that's exactly where you want to walk. Like on what side of the corridor do you want to walk on as you go along each step? And that's just going to go through those polygons, but it's going to be restricted from traveling through any or searching through any other polygons in the world. It's only going to look at this path. Okay. So that's going to give us, that gives us our full ability to do pathfinding. And now Arda is going to talk about how on top of this, we can do other things like building connectivity queries.
Yeah, so I'm going to talk about our connectivity graph. You might know it as label and connected components. Basically, we give each abstract node a connected label, and then we can immediately just look up in the table whether two things are connected or not, if a path exists. So consider the following scenario. You have a bear, and then you have a player standing on top of a roof of a house they've built, and the bear's trying to get to the player. So how is this traditionally handled? Well, the bear is going to do a pathfinding query to the player. Now we know that there's no way for the bear to get to the player, but the bear doesn't know that. Once the pathfinding query finishes, it won't actually reach the target. It will just find a close point to the target. So then what we do is we move the bear as close to the player as we can, and then just throw in some gameplay behavior, hoping that it will handle this case. But if you have a connectivity graph, what you can do is just look up in a table whether the bear can reach the location of the player. And if it can't, just go to some other gameplay behavior. For example, you might just run away. So here's an example of that behavior in action. What we have here is a player inside of a house they've built, and they have a door. Now the door is closed. In this case, the door just cuts off the nav mesh, meaning that the player's sitting in a nav island, not reachable by anything. Now, bound creatures are fully capable of detecting this using the connectivity graph. And what they do is they activate some gameplay behavior to be able to reach the player. In this case, they knock down the door, destroy the door so they can get to you. So here's another problem the connectivity graph helped us solve. During the development of the game, we had a lot of problem with creatures spawning in bad locations. For example, it would lead to things like philosophical bears, acrobatic deers, and NPCs contemplating their life decisions because you can't get down at all. Yeah. Now, using the connectivity graph, what we do is we estimate the surface area of each navigational mesh island, and we only spawn creatures on the islands that we consider to be big enough. So here's something else we can do. Here's one of the cliff sides of one of our forest realms. You can see here that there's many different navigational islands here that are not connected to anything. Now, using the estimate of the surface area size, what we do is we dynamically null these areas out. What this lets us do is it prevents us from spawning creatures there, but also it allows us to quickly detect if a creature ends up in any of these locations and have some backup in place. For example, we can teleport the creature out if we find that there's no way for them to get out. So how would you actually generate this? Well, if you have a static nav mesh, meaning it never changes, it's very straightforward. You just use flood fill using breadth first search, you label everything and you're done. But with a dynamic nav, it becomes a bit more complex. So we do it in 2 steps. What we do is we actually calculate the initial labels using flood fill, just like the static nav. And then as the tiles get broken and repaired, we locally repair the labels as well. So I'll walk you through how it works. Here we have a platform that is off the ground. And then, for example, a player goes there and builds a ramp to that platform. So now they're connected. So this is what the nav mesh underneath with the labels look like. We have 9 abstract nodes with the lines and then the labels there on the left. Because the 2 were split, what we had on the ground is everything was labeled 1 and everything on the platform was labeled 2. The 2 tiles that were just repaired by the addition of the ramp are there in red, labeled 0. And so now what we do is we grab the 2 tiles that were repaired, the 2 nodes that were repaired, grab all of their neighbors, put them in a set, and then for each pair of nodes within that set, we need to find out if a path exists between them. So here it's the bottom left node to the center top. And then what we do is we perform a bidirectional search. In this case, you can see that the path exists. So then we grab all of the nodes that were found during that search and give them a new label because we know they're connected. And then we go through all of the labels that were just changed, in this case, the 1 purple and the 2 yellow, find all the other nodes in the world with that label and swap it over to this new label because we know they're connected. So in this case, you get all ones and you're done. Now, the other scenario is you have the ramp already there and then a player goes and just destroys it. So everything starts with the same label because everything was connected. You have the 2 repaired nodes right there. You grab all of their neighbors again, put them in a set, find out if a path exists between them. Same bottom left to center top here. And then we perform a bidirectional search again, which could, for example, look like this. Now, this is why it's actually important to perform a bidirectional search, because you don't actually know which point is on a smaller nav island. If the ground was much larger, you could be exploring, for example, millions of these nodes before you find out that they're not connected. If you perform a bidirectional search, at most here, you will search only 4 nodes. Now, because we know the platform nodes finished, we grab all of those nodes and we give them a new label different than the ones on the ground because we know it's split. And then we rinse and repeat this algorithm until everything on the ground has a label as well. So that brings us an end to the nav system talk. Now I'm going to talk for a few minutes about how we accomplish what we call living worlds. So the design requirement on us was that realms need to feel alive and teeming with life for players to remain engaged in our game. So here's the challenge. We had to consider you have the following realm template that has been procedurally generated for you. So then how do we place creatures in such a realm to meet this requirement? Well, we were thinking that for the whole realm to feel alive, we need spawning to occur relatively evenly throughout the entire realm. That way, as players go, no matter where players go in the realm, they'll see some creature around. Now, some of the previous things we mentioned, like the long distance pathfinding, we use that for what we call persistent creatures, such as the carnutes that we showed you on repeat there. And we saved that for our more impressive creatures because that's actually quite expensive to just keep creatures lying around the whole time. So we leave them in, they do long distance pathfinding, they're really alive in the world, and the player can just chase them around the world and just see them do their thing the whole time. But to fill the gap, to filling the world with creatures, we use what we call a dynamic spawning system, which I will break down now in 3 points. So the first part is dynamic spawning points. Now, the idea is very simple. It's used all the time in many games and probably just everywhere. What you have here is anytime a player goes within that green circle, which we call like an activation zone, you trigger an event. In this case, the event for us would be just spawn creatures. Now, the trick here is we set this zone to be so large that the player will never actually see the creatures spawn in. This gives them the illusion that the creatures have always just existed there. Now, for optimization purposes, we also have what we call a deactivation zone, which follows around all the creatures that are spawned. Now, if there are no players within any of these zones, then what happens is the creatures deactivate. In this case, for us, we'll just wipe them from existence. Yeah, and then using these dynamic spawning points, this simplifies our problem to actually where to just place these points, which brings us to part 2, which is our points of interest system in the game. So points of interest are a system typically used in procedural games. There are many other games that use this sort of system. The basic idea is that our realm generation team, when they generate a realm template, they also put points in the world that mark them up as points of interest with different radiuses and many other parameters. Now, each of these points of interest are capable of bringing in content dynamically at runtime. So for example, the following is a point of interest that's brought in. Now, a player is able to go through every part of this point of interest, interact with it, grab loot, maybe creatures spawn there, whatever. Now, this is also a point of interest. As you can see, there's actually nothing there. These are what we call data-only points. And the whole point of their existence is that they give us better insight into the structure of the realm. Now, this allows us to spawn creatures in more diverse and better spots in the realm. So then if we mark up all of these points of interest, this is what we get. As you can see, there's just way too many of these points for us to be putting a dynamic spawning point at every single one. The player would be completely overwhelmed with the amount of creatures that would be in the world. Something else to notice is the density of these points. So if you look there at the top left, you might see only 3 points, but if you look at the top right, it's actually quite dense with points of interest. Now, this is why we can't just randomly pick any number of these points and make them dynamic spawning points, because it will lead to very poor experience for some number of players in our game. For example, one player could get all of the points there in the top right and nothing in the top left of the map if you just do like uniform random. This brings us to part 3 on how we made it evenly distributed. We use k-means clustering. So k-means clustering, what it does is it groups all of your data points into just k separate clusters. And the main strength of the algorithm for us was that it gives us relatively even distribution of these clusters all throughout the realm. So we'll show you how it works. So here's all of the data points. How it begins is we pick K centroids randomly among all of the data points. In this case, we've set K equal to 5. For our implementation, we use k-means plus plus initialization for better results, but just for explanation, this is random. And then for step 1 of the algorithm, it calculates the squared 3D distance to each centroid and assigns it to the closest one, which will give you the following. And then for step 2 of the algorithm, it moves the centroid to the average location of the cluster's points. And then you repeat step 1 and 2 until the algorithm converges. So then here you get iteration 2, iteration 3, 4, and 5. And by this point, it has converged. So this is how we actually use it. Here's a bunch of different runs on that same realm template where we've set K equal to 85. How the creature spawning works is we perform this clustering operation, and then for each cluster, we pick one point at random and place a dynamic spawning point there. That means that in this case, we have 85 different dynamic spawning points in the realm. Once the player goes and kills all of the creatures spawned at a given point, after some time, we go and pick another random point within that same cluster and place a dynamic spawning point there. The main benefit it brings is relatively even distribution. And how we can see that is if you look there at the top left of the realm, you'll notice that the clustering is actually pretty much the same throughout most of these runs. And if you look at the clustering at the top right there and in the more dense areas, you'll notice how the clustering is different in every run. That gives us less points in the more dense areas relative to the less dense. It gives us less dynamic spawning points in the more dense areas and more dynamic spawning points in the less dense areas, and it'll kind of evenly distributes out. So to summarize, we showed you how you can add an abstract graph on top of a nav mesh to get longer distance pathfinding with terrain preferences. We also showed you how you can get more efficient custom queries, for example, finding closest unit, and our connectivity graph tech built directly on top of it, and also how you can use k-means clustering to more evenly distribute creature populations in a 3-dimensional space. So I'd like to give a special thank you to the AI team members, past and present, who contributed to the game, the people at the studio who helped with this presentation, and Devin Sigurdsson, who was also a graduate from U of A, I believe about 4 or 5 years ago, who contributed to the development of many of the systems we showed in this talk. Thank you. Please check us out at Play Nightingale. Happy to take any questions. Yeah.
So the roles are part of the template to generate
Yeah.
So how is that? Feel like that finding automated process based on like how is that?
Yeah.
Part of the on the other side is the road.
Yeah. So the question was, how's the road network generated? So that is part of the realm generation process. What happens is we have all of these points of interest and we build the road network to connect all of these points of interest. Now they just have a flag that they can enable, disable to say, don't do that. But yeah, realm generation happens in Houdini and that handles all of the road placement. So basically what we get is every point of interest that we want is connected to every other one through a road network, which lets us do efficient pathfinding throughout the whole world. Yeah. Oh, yeah.
Great thought. You mentioned earlier, well, maybe earlier than that, graph is like exactly. So I assume that the I'd say the essentially the progression kind of factor that you mentioned earlier was probably on the case of quarter, right? I'd say I assume that depends on like a big sector right now.
Yes. Yeah. So the size of the sector plays a big part in all of this. It's a big trade-off in the sense of whether the construction of the abstract graph is the main priority or the repairing of the tiles. So for example, if a player goes and builds structures on these tiles, you have to repair them. And if the tiles are too big, what happens is you're repairing very large sections of the map, which becomes very expensive. So we balance that with wanting more efficient pathfinding queries. And so
also the time to construct the nav mesh to begin with, because the nav mesh, that changes the nav mesh cost. So these are all like things that have to be manually balanced to hit the targets for the game.
Yeah. So how we set some numbers for the tile size was I just did a quick scientific experiment of run it once and with a bunch of different sizes because it just took too long to do it any other way. Yeah. Yeah.
So what I see that is you first particular general first, and then you create the abstract match after all of that as well. I think it's also possible to procedurally generate the match as well. So the nodes and then you build that.
So the problem with that is that there's another software package that's been developed for years and years and years that does world generation. And so it's called Houdini, which I already mentioned earlier. And so that's like a package that everybody deals with. And maybe we could go write a script that tried to do that. But like it has to do with data flow internally. Like Houdini does one job and then we have to sit at runtime and do another job. It'd be really interesting to ask that question of like, oh, I want something that looks like this. Now go generate it for me. But maybe not so feasible. I don't know all the plugins that are possible in Houdini, but
yeah. I'm not.
That's another team.
Yeah. Yeah. On that note, we do offer internships 3 times a year, and our interns do get to work on very interesting projects sometimes. So if you're at all interested, Google Inflexion Games. We have one previous intern sitting in the audience. So hey, right. So yes.
For the spawning points, been able to handle arbitrary functions like appropriating. So people are spatial distance, but maybe there's intricacies, but if you're not something you don't want to do any kind of spawning the side of your example, is there variations to consider on the
Yeah, so our spawning queries we use what Nathan mentioned, EQS, environment query system. So we query the environment and you can put any number of parameters you want in there. So some things we consider is like distance to other creatures, the density of that area, whether it's on proper nav mesh or not, whether it collides with anything, because you don't want a creature spawning inside of a rock, for example. So yeah, there's some things we consider, and then there's higher level things we consider for spawning, such as, well, we want to evenly distribute things. So maybe we say you spawn one thing here, and then that system handles spawning another thing someplace else, if that makes sense. Yeah, so there's like multiple tiers keeping each other accountable to make the distribution happen. Yeah. Yeah.
Thank you for talking. It was very interesting. My question is that what are the typical metrics to evaluate the success of these methods? Do they include any metrics in terms of the user, for example, playability or engagement or believability?
That's a great question.
The CEO plays the game and says, I like it or I don't.
Yeah. Yeah, we have, for like fun aspect, we do like chats every day. We have we have the leadership plays the game all the time. We have play tests. They've been private thus far. But that's how we get feedback on the fun aspect. On the more technical side, for usability, the ideas are relatively complex for most people. So it'd be a programmer or two that handles this navigation in general in pretty much every game that I've talked that I've talked to people about. For example, the expense and how much it saves us. How we decide on these things is I just profile it. So I use the profiling tool. I see, oh, this is how much memory goes up or down. This is how much the cost of a path find from point A to point B takes. It's more of like a, let's run some experiments and find out type of thing there. Does that help answer the question? Yeah. Yeah.
For the agents clustering that you use for spawning and those things. How do you decide the
Yeah, so we set the K to be the number of dynamic spawning points we want. So it's more of a feel thing. Is you play the game and you say, oh, is there way too many creatures? Is there too few creatures? So K sets the number of spawning points, but then each spawning point is also modifiable on what creature it brings in, how many it brings in, all of that. So it's more of like a iteration sort of thing. Well, it could be 85 now, and next week maybe someone says there's way too many, let's bring it down to 75. But that's the basic idea there. Yeah, it's hard coded. And
The realm cards modify that.
yes, yeah. So the realm cards are able to modify that as well. So you say the baseline is maybe 85, and then every minor realm card you play that will modify density brings it down by 10. Now the player has no idea how it actually works. What they get is less creatures in the world, but there'll still be even distribution. Even if you play that card 4 times, you'll still get creatures all over the realm, just less dense. That makes sense. Yeah. Yeah.
So the way that now abstract about this repair every time something happens for percentage, do that areas and the it's also get updated.
Yes. Yeah. So when you repair a tile, it restarts the whole process of building the nav for that tile. It uses a data structure called an octree. It has an octree of each of the tiles. It regenerates that and then creates the polygons based off of the octree in that tile. And the navigation areas are part of that process. Yeah.
In the defense that let's say a search farm is where alcohol is by something. The things can be updated so that it changes.
Yeah, it totally can. We currently don't do that, but that's a great idea. But we do mark up some parts of the map to discourage creatures from going there, going through it. But that's a great use case for what this allows us to do. Is if we just mark that up, then we used to do that with fire, for example. But for a long time, we had bunnies going to the campfire and just burning and dying. And so what we did is we marked it up as a nav area to, hey, try not to go in there unless you're told. And so that helps prevent the bunnies from roasting themselves. Yeah. So it's the same. Sorry? Yeah.
So we change the things previous.
Right now, we're capable of doing that. Yes. We currently don't do that, but we can. There's reasons why we don't do it is because, we want the player to suffer a bit. That's the main reason is you're not just safe because you built something, right? Yeah.
So clearly the abstraction that was being done because was the abstract and you find that we have a lot of better work. It's so sort of near that end where it's a lot of technical verse savings for future sort of years ago.
That's a great question. I haven't spent too much time benchmarking all the different scenarios. Part of the reason is that the dynamic spawning system I mentioned is how the majority of our creatures exist, and they do shorter distance pathfinding. So you're never going to reach, I'm not going to say never, the vast majority of the time, we're not going to reach our budget limit. For the longer distance pathfinding, Like while putting together this presentation, for example, yes, sometimes the paths don't finish in some scenarios. And so we've talked together for a lot of optimizations you can do to make it work. But for example, like heuristics we've talked about and bidirectional search.
A massive number of things that can be done. But as the game gets closer to early access, then we'll start to evaluate like where, like, is it hurting? What are the things that need to be optimized? Because there's no point in optimizing if it's not actually a deal breaker in terms of gameplay. There's so much else that's going on to try and get development finished at this point. Then you've really let the game tell you, or the performance tell you, where it's really critical to get the optimization done.
Yeah, people get mad at you if you spend too much time being like, we have the perfect pathfinding, but then there's creatures falling through the world because your physics sucks, right? So, yeah.
Oh, online question.
Online questions.
It's the second. There we go. Oh, a lot of online questions. If I can just find which way there we go. Okay, blah, blah, blah. I could not hear audio. What about now? Okay, why doesn't increasing the budget for recast help with finding the desired path? So increasing the recast budget would help find the desired path, but there's a limit, right? I mean, when we want to do those long distance queries, we could have doubled the budget, but like it's quadratic in the world. So the budget is only like, because a given path, we're going to tend to have to explore the whole circle. So just increasing the budget is not going to actually have that same improvement. And are the interest points added by human designers, or is there an algorithm running behind the scenes?
The points of interest, they are done procedurally. So the realm generation team procedurally places all of those points based off of the realm template they've created. I hope that answers that. Yeah. Good. We've gone way over time. Thank you for sticking around. Yeah.